For the second problem, I now am given sodium hydroxide volume. So we'll use our same columns here. I know I've got 35 milliliters of 0.15 molar. And let's figure out how many millimoles that is. 35 times 0.15, 5.25 millimoles. And here I've got 17.5 milliliters, 0.15 concentration. Let's see how many we have here. 17.5 times 0.15, 2.625. All right, so we can see that our limiting reactant is our sodium hydroxide. So let's subtract minus 2.625 minus 2.625. What does that get us? 5.25 minus 2.625. Oh, exactly half. So we get 2.625 millimoles, and that's of our acetic acid. But remember, we know that acetic acid is going to form this conjugate base over on the right side. We know that Na is just a spectator ion. We can cross that off, right? We know that if I'm losing reactants, I am also gaining, this is under my acetic acid column, or my acetate ion, I am gaining 0.625 millimole of my base, my acetate. I'll write it up here, C2H3O2. So this looks like, if I know concentration or amount of acid and base, and we want to find the pH, this looks like a Henderson-Hasselbalch equation, where the pH is equal to the pKa plus the log of my base over acid. So we're just going to do the pKa, so we've got the negative log of my Ka for acetic acid. We look it up, and we just looked it up, I guess, in Appendix D, 1.8 times 10 to the negative 5, plus the log of my base, which is 2.625, over my acid, 2.625. The same number, so they're going to cancel right out. So to find the pH, just the negative log of 1.8 times 10 to the negative 5th. 4.74 pH units. This next one, we have 34.5 milliliters of our base. So we know that we've got the same going on here. So I'm just going to write down here that we have 5.25 millimoles. Nothing changed. Here we've got 34.5 milliliters, 0.15 molar. So let's find out how many millimoles we have of our base. So 34.5 times 0.15, 5.175 millimoles. So we can see here that my base is still going to be my limiting reactant, minus 5.175. I have no base left, minus 5.175. We're going to do 5.25 minus 5.175. We'll have 0.075 millimole of our acid left. Now, remember, when I'm losing reactants, I am gaining product. And my product in this case, I have a conjugate base, right? So for my acetate over here, I'm going to add 5.175 millimoles. And now that I've got a base concentration and I have acid concentration, I can use my Henderson-Hasselbalch. again, where I can do the negative, or the pH is equal to pKa plus the log of my base over acid. So let's plug in our negative log of 1.8 times 10 to the negative 5 plus the log of our base, our conjugate base, 5.175 over the acid, which is 0.075. Let's see what we get. Negative log of 1.8 times 10 to the negative 5th plus the log of 5.175 divided by 0.075. And we get a pH of 6.58. So I'll write that over here. pH is 6.58 units. So our pH has increased. It, starting at 0, 2.78. Add some base, it became more basic, 4.74. Add some more base, it's up to 6.58. Let's see what happens when we add another half of a milliliter, so 35 milliliters. Let's look at this next one. We have 35 milliliters of base. Now I've been doing this whole time, 35 milliliters of acid at 0.15, 35 milliliters of acid, 0.15, all the way on down. We know that that gives us 5.25 millimoles of our acid. Now we're also saying we have 35 mils of 0.15 molar base, which also will equal 5.25 millimoles of our hydroxide. So we can see here that, well, they're both equal, so minus 5.25 minus 5.25, they're both going to be used up equally. We don't have a limiting reaction in this case. But we can't say that this is a pH of 7, like when I had two strong acids and bases, because we know that this is going to create, if I'm losing it here, I'm gaining it over here, I'm creating acetate. So I will have plus 5.25 millimoles of my acetate. Now this is where the chemistry happens. Because we know acetate will undergo hydrolysis. If I looked at and draw, I know that we're running out of room here, but that's okay. We're going to be okay. If I write my acetate, C2H3O2, undergoes hydrolysis, it forms an equilibrium. The H from the water is going to be donated back and form my acetic acid and hydroxide. Now, when we look at this, I don't have a Kb value for acetate, but I do have a Ka value for acetic acid. We just looked it up. It's 1.8 times 10 to the negative 5. So we can find the Kb since we are calculating base. That's why we need a Kb. So we know that Kw, the ion constant for water, is equal to Ka times Kb. Well, I always know that this is 1 times 10 to the negative 14th, and I know my Ka, so I can do Kw divided by Ka to get my Kb. So we just need to do 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 to get our Kb value of 5.56 times 10 to the negative 10. So what do we know here? We know that I have 5.25 millimoles of acetate. And we know that I have that much acetate in a combined volume of 35 milliliters of base and 35 milliliters of acid. So in 70 milliliters. So that gives me a molarity of 5.25 divided by 70 0.075 for my concentration. I now can say, okay, I know my concentration of acetate. I don't know this and I don't know that. So let's do our K, using our KB, we can set that equal to our products, x squared, over reactants, 0.075. Let's solve for x, which is our hydroxide ion concentration. So 5.56 times 10 to the negative 10 times 0.075. Let's square root it to get x. And we get x, which is our hydroxide ion concentration of 6.46 times 10 to the negative 6. Now to find the pH of this, I need to do 14 minus the negative log of our hydroxide. 14 minus the negative log of our answer. And we get a pH of 8.81 units. Now this next one, so we just got done looking at having the exact amount and concentrations of each. So we've hit that equivalence point where they both are used up at the same. Now we're going to overshoot that. We're having a half of a mil more. So again, it's okay that we're under here. We're going to move E down. So we've got 35 milliliters of 0.15 concentration for our acid, 35.5 milliliters of 0.15 molar for our base. Let's see what we get here. We know this is 5.25 millimole, and this is going to be 35.5 times 0.15, 5.325 millimole. So we can see here, my acid is my limiting reactant, minus 5.25. And we can see here, I have excess of my base, 5.325 minus 5.25. I have 0.075 millimoles of my base. Remember, this is my strong base, my strong straight hydroxide. This is going to trump anything that we have going on, right? So I've got 0.075 millimole of my OH minus. I know that I have a combined volume of 35.5 plus 35, so 70.5 milliliters. I can find this concentration, find the negative log of that, and do 14 minus that to go straight to pH. So I can do 0.075 divided by 70.5. That's my concentration of my hydroxide. So let's do 14 minus the negative log of that answer to get a pH of 11.03. All right, there is one more. We have 50 mils of our base. So I'm going to draw a line here. This is our 50 milliliters. So we've got the same acid. I'm just going to write down our 5.25 millimoles. Here I've got 50 milliliters times 0.15 M to get 50 times 0.15, 7.5 millimoles. So this is going to be similar to our last problem where we're going to have excess base. So we can see here that my acid, 5 minus 5.25, I do not have any leftover acid. So let's do 7.5 minus 5.25 to get 2.25. And since this is strong, I'm not worried about any kind of Ka or Kb chemistries. This trumps all. So we're going to take my 2.25 millimole divided by my total combined volume, 50 plus 35, so 85 milliliters to find this concentration of my hydroxide ion. 2.25 divided by 85 gives me a concentration of 0.02647. This is my hydroxide ion concentration. So let's do 14 minus the negative log of ROH, 0.02647, to get a pH of 14 minus the negative log of my concentration, 12.42 pH units. So going back to kind of look at what we did, up here I started with acetic acid and no base. And so because I did not have any base, we were looking at acetic acid. That's has a Ka value. We know that that acetic acid is going to dissociate into H plus and acetate ions. So in order to find the pH, we needed to know the concentration of the H plus ions. So we did products over reactants using a Ka problem. For the second one, we saw that, yes, we were given some base, but that was our limiting reactant. We had acid left over. So we know that because of the hydrolysis that's happening, since I have some acid, but I also have some of the conjugate base being produced, since that's a product. So I've got some conjugate base, I've got conjugate acid, so we're going to use our Henderson-Hasselbalch equation, because we've got base over acid, conjugate base over conjugate acid. Then we get to a problem where, see, the last two we had no base left over. This one, oh, I guess our base was still a limiting reactant. So if we had excess acid, again, we're going to have that conjugate base, same Henderson-Hasselbalch. Then we get to the point where we have equivalence point being met. We have exact same amounts of acid and base being used. So we know that, well, the only thing that's being left and that's being made is our acetate. So that becomes a Kb problem. We took our acetate, underwent hydrolysis, it produced the conjugate acid and hydroxide. We needed to know the hydroxide so we could find the pH. If we had hydroxide, we can do 14 minus the negative log of our hydroxide that we found to get pH. For the next one, we're given just a teensy bit more, so more base, because we were equal here. Now we have excess base. When we have excess base, we don't need to think about Kas, Ks, Bs. The base in its pure raw hydroxide form is going to trump. We only care about that. So we took that millimole divided by total combined volume to get its concentration for hydroxide, did the negative log of that, and then 14 minus that to get our pH. And then the same thing for the very last one. We just had an even larger pH.